And
doing your offer.
You're going for the top shelves, right?
yes, Max. And you know, there's sort of some caveats on this condition. We might this not go forever, so in that case we'll append some discount factor. And we kind of want to maximize the overall trip over all trajectories. So really we want to maximize expected value of the quantity. And so
we have hexagonal ships, is that more appropriate, like more sci-fi or something?
hexagonal, yeah. So hopefully that will make sense. They're pretty similar. So the difference would be that with operations research, often we know more about these states. And we can kind of prove in some cases that our policy is optimal. Whereas with RL, no such luck.
Just right.
Yeah, but in principle, it's operations research problems can be viewed as RL problems, but there's sort of special cases that permit more efficient.
Yeah, that makes sense.
Cost to the spring before. For some reason it wants to cost to vanish through. Why does it do that? That's not right.
I guess the other thing is that maybe in OR, oftentimes we only need to make one big decision. Like if we're doing, say, or rather the decisions don't have this sequential element necessarily. So say for example we're doing routing, then like the route we follow today doesn't impact the route we follow tomorrow.
Right.
So if like if we're doing maximal matching, like hacking on these
previous lectures, so for
impact on future decisions.
Alright, so for whatever reason.
But here, the action you take at A0 can affect the future state.
Is not supported.
Yeah. So there's this big time factor. Anyway, that's my
first Andre's lecture.
So that's my inadequate introduction to the field. I think it captures the objective if nothing else.
And Peter's lecture from earlier,
This
where he
is
talked.
absolutely crazy. We don't have there's no HDMI connection here, is there?
Chromecast on right now.
Nope. It's not happy. It'll, not on this one, I think. The other side. What is it called? Oh, we've got 2 viewers. Hello! Fantastic. Patrick, could you maybe try and cast that I watch the YouTube live stream so that we can capture questions?
Yeah, sure.
Questions like, why aren't you starting?
Oh, yeah, that's it. One question I have is, what are we covering?
What? I slacked you what we're covering.
Alright, natural policy grades.
Yeah. It's a 40-minute Truman lecture And we can, if we have enough time, we can even go through the internet at least. Yeah. That's fine. So now we're obviously live.
Bootcamp.
But someone already dropped off. That's 3 watching now. Okay, that might be me. Cool. The link should be on the page.
Is there some kind of friend distributing Mel Ryan?
Yeah.
Awesome, thanks Matt, appreciate it.
Alright.
Talk soon. Bye.
Sorry, I'm taking over the time.
Alright, hi everyone. I'm John. I'm going to build on 2 of the previous lectures. So first Andre's lecture and Peter's lecture from earlier where he talked about active grading methods. So I'm going to talk about more advanced optimization methods using only policy gradients. So what Andre just talked about in the last lecture is he calls a vanilla policy gradient method, because it's essentially just getting a policy gradient estimate and plugging it into stochastic gradient descent. And there are various ways of modifying that and bells and whistles you can have. Like Peter talked a lot about these active break methods that use the value function to get a lower variance advantage estimate. So you can do a lot to get better advantage estimates. But I'm actually not going to talk about how to get better advantage estimates. I'm going to talk more about changing the underlying optimization algorithm. Once you compute your advantage estimate, how do you update the policy with that? And so I'm going to, and essentially this is for 2 reasons. There are 2 things we need to improve on from the vanilla policy grading methods. One issue is that it's pretty hard to choose good step sizes for them, and to choose a single step size that's going to work over the course of the whole optimization process. So, in reinforcement learning, one difference from supervised learning is that the data that your network is receiving as its input is not stationary. And that's because as your policy changes, you see a different distribution of observations of rewards. So that means, so you might, for example, be getting 0 rewards for a while, and then at a certain point your policy randomly gets a positive reward, and then your reward starts going up. So what that means is that the statistics of your inputs are changing. So it's hard, that makes it really hard to choose a good step size, which is going to work over the whole course of the process. And you can address that somewhat by normalization techniques, but remains a problem. So another issue with the step size is that if you take too big of a step or a bad step,
These do fall off in like what do you want to do? Like you have to make a choice. We don't have any way to
if you mess up your policy, then you're going to start collecting bad data. Like if you change your policy by too much, then you're going to collect. You're going to visit a totally different part of the policy. You'll have a bad policy, and then you won't be able to recover because all the data you're seeing is from the bad state. So you can have a disastrous drop in performance if you take a bad step. This makes it really hard to design a nice and stable algorithm. Another issue with the vanilla policy grading methods is their sample efficiency. If you just when you collect some data, if you just use them to compute a single gradient and then throw the data away, you're probably not getting all of the available information out of it. And you can see that especially well if you imagine that your network is scaled poorly. Like, let's say some of the gradients are 10 to the 5 times bigger than other gradients. I mean, gradients on some components are bigger than the gradients on other components. Then you're going to make very little progress on the ones that have tiny gradients, and you're just doing normal stochastic gradient descent. So you might, so anyway, you might have really slow learning, and we might be able to do better at this by using a more sophisticated kind of optimization method. Instead of just taking a single gradient with the data, you can solve some little optimization problem whenever data comes in. So I want to make that point in a slightly more philosophical way, or describe what we kind of want to do here. So if you think about a lot of modern machine learning, a lot of it's about reducing the learning problem to numerical optimization. So learning is about being able to make some kind of prediction on data you haven't seen before. And what deep learning is all about is writing down some kind of numerical optimization problem and then using some kind of gradient descent algorithm to approximately solve it. And in supervised learning, you're just minimizing training error. And what you really care about is test error, but if you minimize training error, that's usually pretty good, especially if you tweak regularization and things like that. So in RL, the situation is not as clear cut. So we'd like to write down some kind of optimization problem we can solve, which uses all of available data that we've seen so far and computes the best policy from that. But it's not clear how to do that. What optimization problem should we write down? So Q-learning is actually quite nice because you can take any set of transitions from your dynamics model and you can fit a Q function using them. You can try to fit Q star because the Bellman equation makes sense no matter what policy your data was sampled from. So that's pretty nice, but this comes at a cost of actually optimizing the wrong objective. So for Q-learning, you're trying to...
All good?
Yeah, I was just wondering, because you mentioned that the policy gradient method is like, it's gradient descent, but no optimization problem. Then how can we find out the best policy
Right.
to execute? Or am I misunderstanding?
Can you repeat the question?
Because I mentioned that there's like no optimization problem in RL for the policy gradient method. So, what my understanding is that you want to find like a policy or like best policy to actually execute to like go to the next step, right? But if you don't have an optimization problem, then how do we decide?
Yeah, it's a good question. So I'm just going to write down the reinforce algorithm, which is like so step one, assume I has parameters theta while I'm on board generate a sample trajectory using I theta 2 update theta as theta t plus 1 plus theta t plus plus alpha times the gradient of log pi theta times gt, where gt is 10. So this is saying that we're generating a trajectory, and we're doing a version of gradient descent based on samples that we collect from our environment. But there's no explicit optimization problem we're trying to solve. It's not like there's no way. There's no like loss function involved, right?
Yeah.
It's just we're continually updating our policy, and we have a return, but this return is stochastic. Like, so we never know whether it's optimal.
Right, okay. But how, sorry, I still don't, how do you compute this policy?
Well, we can, so I think, so this technique, the reason why this works is called the log derivative trick. The idea is that if J let J of theta equal the expected value of pi of what? Of return? GT? Yeah. Then grad theta J theta is equal to the expected value of pi of grad of log pi.
Yeah, but that's not good from this to how you get the last one.
And this is called the log derivative trick, which I'm not going to get into. But that
I mean, do you know what it is? The log derivative trick? Or just basically probably it's better just to mention this.
Alright.
Please.
Alright.
And then we do just this equals 1, right? And then we'll just put this in here.
Alright.
But then that this is grad log and right. Yeah? Now we can finalize and we start the work. And that's and this return, if you then write down the integral, you get like so probability of trajectory multiplied by the return of the trajectory, right?
Yes. Yeah.
And then you can put gradient to it, and your probability the trajectory is parameterized by your policy, because by policy basically tells you what action to take, right?
Yeah.
So after you apply these two things, the knowledge of, like, you have this probability of theta of t over here in your integral, and then you apply this thing here and end up basically something like that. I mean, we could explain it.
Is your question like more basic, like why can you optimize this at all?
But I mean, like, it's more like you would have like an objective to take to the next action, right?
Yep.
And if, I mean, you do want to try to find like which way or what action you want to take, right? That,
Yeah. So that's done by the policy part.
yeah.
And then this reinforce algorithm.
The expectation return. So as long as it's increasing in expectation, it's getting better on average.
Oh, okay.
Is that was your question? Because it's an expectation of the return. It's not just one single.
Yeah. Okay. So if the expectation is increased, then we could.
Yeah.
Okay.
There's a lot of noise going on.
Yeah,
but
yeah.
As long as you take the expectation,
And it actually is increased, then we decide, okay, yeah, that would do, and then we just keep going.
and you sort of follow that
Yeah, okay,
signal
that makes
in
sense.
the expectation.
Yeah, sorry. Yeah, okay.
All good.
That makes sense.
Yeah, and I think the point of like no optimization problem is that we never actually bother computing the expectation. We just rely on single samples and continually update.
That makes sense. Sorry.
We don't compute gradient itself, right? We just estimate it. That's the whole point. And that's why we. No. But we estimate it, right? Because if we compute it, if we could compute it, we would compute it over the integral, right?
Right. We can't
But
compute
then
it.
we use estimate. But then we use expectation. But then we use Monte Carlo.
Yeah.
And this is inequality comes where
Right.
it comes here, and then there is no like true gradient we can rely on. It basically tells us the direction, but it doesn't tell us about the value of like how big our step size should be, the direction,
Right.
isn't it? But then we use second order derivative, blah blah blah, just to complete the rest.
Yeah, that's
It's
exactly
just
why we're
for
watching
this.
this lecture. Because if I remember correctly, one of the reasons that PDO was introduced was to get rid of all the second derivatives. Yeah, because it would be more precise if we could do all of this stuff easily, but apparently the second derivatives are just not worth it.
It's like a less intense way of doing this that sort of thing.
I'll slack you a more comprehensive introduction to this. But yeah.
What was the, where did you get that algorithm from anyway? Because that's not the same phrasing as in the book.
Oh, I got it from a blog post.
Oh, okay.
I'll post it this thing.
Okay.
Meeting.
Dennis, give me your email address and I'll invite you to this lecture.
Yeah, Q Dennis Q.
Q Dennis Q, sorry?
Yeah, Q Dennis Q.
Is it Dennis with one N or two N?
With one.
So Denise?
Exactly.
At?
Gmail.
What's your last name?
Shit.
How do you say it?
Like literally like shit, and then LV.
Oh, V. Okay.
Yeah.
I'm just hard of hearing, that's all. Like, I'm just a little bit. Nothing against your name. Okay, you should record my invitation.
Thank you.
Really? Shall we continue the lecture?
Yes, please.
Minimize some kind of Bellman error when what you really care about is that your policy performs well. So policy gradient methods are, in contrast, actually optimizing the thing you care about, which is the performance of the policy. But the downside is that they're not as good at using old data or at using all the data you have available. So this lecture is going to improve a little bit on the vanilla policy gradient methods, where instead of just taking our gradient estimate and taking one step with that, we're going to actually write down a little optimization problem based on the data you collected from your current policy, and we're going to solve that optimization problem approximately. So we get a little bit more information out of our data this way. It's still not perfect because you can't take all the data you ever collected, but it's an improvement. So then the next question is, what loss should we be optimizing? So we want to write down some kind of loss function to define a policy gradient method, but what kind of loss should we use? So first, let's just look at our vanilla policy gradient formula. So here we have, this is just one way of writing it. We have some kind of expectation. The hat means this is an empirical estimate expectation, meaning we collected a bunch of time steps and we're averaging over them, so we're averaging over t. And we take grad log probability of the action times the advantage. Okay, so that's our policy gradient formula. And well, we can write down the loss function such that differentiating that gives us the policy gradient. And the loss function we want to write down, one choice is we just write down log probability times advantage estimate, which is treated as a constant. So obviously if you take the gradient of that, you get our policy gradient estimate. And this is actually what you want to do if you want to implement policy gradients with an autodiff library. What you should do is just write down this loss and then differentiate it. Okay, but the thing about this loss is it doesn't actually make sense as a loss that you can do many optimization steps on. You don't want to optimize this to convergence because let's say the advantage is positive. Then you're going to try to drive the log probability to infinity, or you're going to drive, well, if it's a discrete action space, you're going to try to drive the probability to 1 for that action. Or if the advantage is negative, you're going to drive the probability to 0. But the advantage estimate is noisy, so so you might have just gotten a noisy estimate, and you're going to radically change your policy based on that, and that's probably going to make your policy worse. So this clearly isn't exactly right. Well, I'm not going to fix that problem yet, but I'm going to say there's another version of this that's also interesting to look at and gives us the same policy gradient estimate. So instead of writing it as log probability times advantage, we can write it as this probability ratio times advantage. So if we write down this ratio and then we differentiate that, we get the exact same gradient. And that's just because of the chain rule. So if you have grad log in some function, the gradient is just grad of the function divided by the function value. So anyway, this formula is just as good. But this formula also has an interesting interpretation in terms of affordance sampling. So one thing that's pretty sensible to do is to say we're going to sample. We're going to collect data from some policy, which I'm going to call pi sub theta holds. And then we want to, let's say our new policy, which means our updated policy is called pi sub theta. So one sensible thing to do is we want pi sub theta to have pi expected advantage. So we want like policy pi sub theta to take positive advantage actions. So we write down this expectation, and then we do affordance sampling. So in affordance sampling, affordance sampling lets you say what would the expectation be under one distribution, even though I collected samples from some other distribution. So anyway, you can do affordance sampling, and then you arrive at this formula I wrote on the previous slide. So it basically says we want to choose a policy pi sub theta such that the expected advantage under that policy is high. Where we still are collecting states from the old policy. Anyway, I don't want to get too bogged down on this. But anyway, this doesn't solve the problem with.
We were just sitting in this room that we put in a description all the time from like 4 o'clock. I will bring my stuff.
Awesome.
I didn't actually talking about other things.
Into the room, so yeah.
We got another scene.
Thank you.
Okay. Yeah. Doing no, nothing here really. Just going over policy gradients again.
Yeah.
Writing down loss functions.
Mm-hmm.
Yeah.
That's the sort of loss that we talked about last time already.
The what?
Well, not last time, I was here.
Yeah.
Yeah.
Yeah, we talked about this one. PPO.
Yeah. By the way, A stands for advantage. It's the actual return minus the estimated return.
Yeah, it's the average over all actions.
No, it's Q minus E.
Okay, minus the. Alright, right.
Yeah, where V is actually V. So.
Alright.
So.
Yeah.
Oh, there are some of them. Just
Alright.
Chris, you want to be here?
Sorry.
I just got on.
Okay. Did you want to be here?
So Q is the expected return given that we're in this state and we're taking this action, and B is the is there a match there? Or, no, it's fine. That's the expected value.
Yeah, it's the sort of the pi expected value over steadiness.
How much better is actually better than that?
Yeah.
So advantage will be positive for good actions and negative for bad actions. And this is a way of reducing the reducing the variance without changing the bias.
Yeah.
That's the big problem so far. I mean, we can take a gradient step on that, and if it's a small step, we're okay, but the big problem is that we don't want to optimize this objective fully because then we're going to do too big of an update. Here's a way to solve that issue. So the way to solve it is to use what's called a trust region. This is a well-known kind of method in optimization where you say, I have a function I want to optimize, and I have some local approximation of this function which is accurate locally, but it gets really inaccurate if you go far away from your starting point. So we have some kind of trust region where we trust our local approximation, and as long as we're in the trust region, we're willing to optimize our local approximation a lot. But if we get outside of that, all bets are off. So the way these kind of methods work is you say, I want to optimize this objective, which is our local approximation, subject to some constraint that we're not moving too far away from the starting point. And there are lots of ways we could define this constraint. For example, we could say that the Euclidean distance between our starting point, theta olds, and our final point, theta, is small. So that would be one way to do it. But instead of using Euclidean distance, we're going to compute the KL divergence between the old policy, pi sub theta old, and the new policy, pi sub theta. So that's what we mean by this KL expression here. So this is just a distance. This just is a way of measuring the distance between probability distributions. So the nice thing here is we're actually looking at the distributions that the parameter vectors determine, as opposed to just looking at the parameter vector, where it's not clear what's a sensible update in parameter space, like how big of an update should we do in terms of Euclidean distance. That's pretty hard to say because we have some really complicated function that's going from the parameter space to the output space. But in terms of KL divergence, KL divergence is a unitless quantity, and it has a nice interpretation. So we're basically saying that the probability shouldn't change too much. The action probability shouldn't change too much. And so that's something that's that's very robust, and it's not problem dependent. So we can define some hyperparameters that make sense over a wide range of problems. So anyway, what we do is we say, recall that this expression just gives us the policy gradient. So if you differentiate this objective, it's just going to give you the policy gradient. Yeah, I mean, this comes out of some theory, but actually it doesn't make a difference in practice. So yeah, I mean, you can actually we're going to do an approximation later to the KL, and it actually the ordering doesn't really matter. Okay, so anyway, this is the constrained optimization problem we want to solve, and it's also worth considering that we could solve a penalized optimization problem instead of a constrained problem. So we could have said, let's just penalize the KL divergence instead of putting a hard constraint on it. And according to the method of Lagrange multipliers, this is essentially equivalent in that if we want to solve this problem, the solution also, it's a necessary condition that it's also the solution to this problem. Let's see, I had a couple of questions. Oh yeah, so the question was, have people tried to use different distances like Wasserstein distance and so forth, which have been used for GANs. So actually it isn't going to make that big of a difference what distance you use here, because usually we use pretty simple distributions over actions. So any kind of distance on probability distributions is going to do the same thing. Like, there's not too much to say about different distances between Gaussian distributions. If you started to use more sophisticated distributions, then that might be relevant. Another question? Oh yeah, so the question is why use the penalty instead of like the hard constraint? Actually, I'm going to talk about the trade-offs between these two things later. I'm just saying here that it's equivalent in a certain sense because we can choose some data so that the solution for any given like hard constraint, we can get the same result by using the penalty. Okay, I'm going to move on. So anyway, so it turns out that there's actually a theory result that pertains to this penalized objective. So it's not exactly the version I wrote down on the previous slide, but if you take a max over state space instead of a mean over state space, and so you constrain the max KL between the new policy and the old policy over all state space, then it turns out that you get something that's actually a lower bound on the performance of the policy, pi sub theta. So the point is, let's say we sampled some data with pi sub theta old, and now we want to get a new policy, pi sub theta. So we want to write down some objective such that if we maximize that objective, it'll actually improve the performance of the policy. So it's not totally obvious how to do that because if we just take some approximation to, I mean, we don't have analytic access to the performance of the policy because to calculate the performance, you need to interact with the environment. So we just want to write down some kind of objective that we can do numerical optimization on and doesn't involve interacting with the environment. And it's not clear that we can do this. But it turns out that that we actually can write down an objective which is a lower bound on the performance of the policy. And that involves a max of the KL over state space. And if we maximize that, then we're guaranteed to improve the policy. And we can illustrate that with this diagram here. So let's say eta, this red curve, is the actual performance of the policy parameter theta. Then if we compute this surrogate loss, which is the thing before we added the constraint or the penalty, then, okay, this is a good local approximation, which has the same gradient. But then if you go too far away, all bets are off. Like if we try to maximize that, we'll go all the way over here. So then if we add in the penalty, we end up with this blue curve, which now becomes a lower bound of the performance. So if we maximize this blue curve, we end up over here. And since it's a lower bound, that means that we're going to make more improvement on the real thing than we did on the lower bound. So we're guaranteed to make at least as much improvement on the real performance if we optimize this lower bound. So that's pretty nice that we can actually take some kind of non-trivial policy update and be guaranteed to do improvements to the policy. In practice, the theory, we have to make some approximations of the theory because it's way too conservative in how, like, what kind of update it tells you to do. It tells you to do way too tiny of an update. So we use the mean of the KL over state space instead of the max KL, and we also, let's see, we do an empirical, a sample-based approximation to it, and we also take a bigger step than the theory recommends. So anyway, putting this all together in pseudocode, the way it looks is each iteration, first you sample a bunch of data from your policy. So you run your policy for t time steps or n trajectories. This is using your current policy. Now we go back and look at all of our trajectories or trajectory pieces, and we go and compute the advantage function at all time steps. So then we've got this advantage function, and then we write down our constrained optimization problem, which is maximize the surrogate loss subject to some constraint. And then it turns out we can solve this constrained optimization problem efficiently using conjugate gradients. And I'm going to describe how to do that later. We can solve it approximately. We're not solving it exactly. And then we repeat. So this is an iterative process. And this is similar to some other methods like natural policy gradient and natural actor critic and refs. So this idea has resurfaced many times and will continue to. So now I'm just gonna talk a little bit more about how you do this efficient solution using conjugate gradient. So this is actually not new to this method TRPO. These are some kind of well-established methods for numerical optimization. The idea is that you have some kind of problem, nonlinear optimization problem you want to solve. So what you do is you repeatedly make an approximation to it and then solve that subproblem. So we're going to make a pretty aggressive approximation to this the nonlinear optimization problem, where we make a quadratic approximation of the constraint and a linear approximation of the objective. And we solve these quadratic programs, and then we do that efficiently. But anyway, let's just look at the penalized version of the problem and look at how to solve the penalized version. So first we're going to make a linear approximation of the objective and a quadratic approximation of the KL constraint. Note that the KL constraint kind of just looks like a quadratic distance function. So the KL divergence has, it has zero derivative at your starting point because it's minimized at your starting point. So the KL has two arguments. It's like the distance between two probability distributions. And the distance is minimized. If you look at varying one of the arguments and keeping the other one fixed, the distance is minimized when you're at the starting point, and it goes up smoothly as you go away from it. So it looks like a kind of quadratic distance function. But we want to figure out exactly what the matrix is that defines this quadratic distance function. So we're going to make this approximation of the problem, and this is just the Taylor series kind of expansion, the second order, around theta olds. And and these are, so we want to make this linear, this affine approximation of the objective and quadratic approximation of the constraint, and that's because it turns out that, well, I won't go into all the justifications. And anyway, the solution to this is just like it's just a constant multiple times this matrix F inverse. That's F is our Hessian times G, which is the gradient. So as it turns out, the F here is called the Fisher information matrix. This is something that appears all over the place in probability theory. It's sort of telling you how sensitive the probability distribution is to different directions in parameter space. So it's telling you if I move in this direction in parameter space, how big of a change to the probability distribution is that. So anyway, this step that you get when you solve this quadratic program is called the natural policy gradient. So anyway, we somehow, this is all well and good, but we don't want to compute this, we don't want to compute the whole Hessian because it's really expensive to compute a Hessian. Like computing the gradient of some scalar value function is only a small multiple times the computation cost of computing the function itself. That's a kind of the principle of the cheap gradient principle. But computing the Hessian is way more expensive. It's effectively, you have to compute.
I don't understand where, so I understand that the first order derivative of the KL divergence is 0, right? But this, so the sort of the likelihood term in this loss function should have a second derivative as well, right? I don't see that. It looks like only the KL divergence is a thing that picks up the second order derivative.
Right.
don't understand why.
Make linear approximation.
Isn't that because it just simply says it's negligible compared to KL, so therefore it's
Oh.
not, it exists, but it's
Oh.
it's good enough, it's zero enough.
Right, so that's
So what's the Fisher influence?
right. Yeah, so, okay.
With the Fisher information matrix from the description, I've never heard it before on this one, so from the description it makes sense that it's the hashing here, but is it just, it sounds like because it gives you information about the direction that something moves, so why would that be any different? Is it always the hashing?
No, the Hessian just means the second order derivative.
Yeah, exactly. But so it's not like the Fisher information matrix is always the hashing of something else. So that's how you get it. Or
Yeah, no, it is.
Oh.
Of the log probability, if I remember correctly. And
The second derivative of the log probability. Right, so it's the Hessian of the log probability. Right. Okay. And then there's this theorem that says that we can make a metric based on back-Clyde divergence. Great. So G is log likelihood.
No, G. Well, yeah. Sorry. Yeah. So it's typically the negative log likelihood contribution to the in quotation marks.
Okay.
Okay. Yeah. Sorry, I didn't read that. But so the quadratic part of the second order derivative of L doesn't really contribute as much as the K divergence does.
F is positive semi-definite, but not if we include Hessian, so that might be another reason to get rid of
Right.
L, the Hessian of L, because I like my loss functions to be positive.
Yeah, because then you can just take the numeric analysis.
Yeah. Cool. Alright. Good old Taylor's theorem.
Yeah.
Shall we continue?
Yep.
So,
N gradient if you have n parameters. So that's really bad. So yeah, we could go ahead and compute this hashing, but it would be really expensive. So okay, anyway, I'll skip this because it's not that important. That section on the I must have deleted that slide by accident. That's funny, I had it in my slide. Okay, anyway, what I was going to say is that you can, if you can actually compute this, this expression F inverse G without actually ever explicitly forming the matrix F. And this is a pretty neat idea, and this is using the conjugate gradient algorithm. You can the conjugate gradient algorithm is a way of approximately solving linear equations. So in this case, the linear equation we want to solve is fx equals g. So conjugate gradient algorithm will approximately solve this linear equation without ever explicitly forming the matrix F. Instead, it just needs to take a bunch of matrix vector products. You just need to define some function that takes a vector and it computes f times x. And then you call that function a bunch of times, like 10 times, and conjugate gradient algorithm will approximately solve this equation. And as it turns out, so how do we get this function that does the matrix vector product f times x? Well, it turns out if you have a regular old reverse mode autodiff program like TensorFlow, you can do that. And you can just write down the gradient vector product, and then you differentiate that to get a Hessian vector product. Anyway, you can check out the textbook Numerical Optimization by Nosidal and Wright, which has a really good explanation of this. idea, which is used a lot in nonlinear optimization. So that's what we use here. It sort of appeared in the deep learning community called Hessian-free optimization, maybe 5 years back or so. And then it was used in the trust region policy optimization in the deep RL setting. So anyway, that's what TRPO is. Let's see, do I have a slide of that? Okay, anyway, I already showed you this pseudocode for TRPO. So let's see. Okay, so a summary of what I just showed you is, okay, we want to optimize, okay, we wanted to write down an optimization problem, which would, we can solve to do a policy update. And this way we'll get a more sample efficient and more robust algorithm than a vanilla policy gradient method. So we want to write down some optimization problem. So the first suggestion is to just write down some kind of loss that when you differentiate it, you get the policy gradient. So we got this LPG, which is just log probability times advantage, and LIS, for important sampling, which is like this probability ratio times the advantage. But that's no good because it doesn't actually constrain the size of your update in any way. So instead, we suggested to use the KL divergence to constrain the size of the update. But then we have a constrained optimization problem, which is harder than just solving an unconstrained problem. So we suggested instead, so we noted that when you do a quadratic and affine approximation to this problem, you get the update step looks like F inverse G, which is, this is the Fisher information matrix, and this is the policy gradient. This is the same as something that was proposed previously called the natural policy gradient. And we can solve for this step approximately using the conjugate gradient method. And TRPO also does a line search on the original constrained optimization problem to make sure that the update that you did is actually a good, improves the objective in that constrained optimization problem. Yeah. 10 minutes. Okay. Let's see. So there's also another version of this that's worth knowing about, which is in which you don't actually use the conjugate gradient algorithm, but instead you directly look at the penalized version of the objective. And this is useful if you either don't want to do the conjugate gradient algorithm because it doesn't work in some setting, or I don't know, in some cases this might work better. But anyway, the idea is we're going to work directly with our penalized objective, and then our pseudocode is that we first collect data from our policy, we estimate the advantage function, and then we just do SPD or LBFDS, any old unconstrained optimization algorithm on this objective with the KL penalty. So that's an easy thing to do, but the problem is it's hard to choose this coefficient beta in a way that it works well over the whole course of the optimization. So what we can do is we can instead just choose the KL divergence as our hyperparameter, and what we do is we adjust our penalty coefficient beta to try to make the constraint satisfied exactly and tightly. So basically, if we took too small of a step, so after we did our optimization, if our
this is a stupid question, but is that state beta?
Yeah.
Oh.
We did that before.
If the step was too small, we reduced the penalty coefficient, and if the step was too big, we increased the penalty coefficient. So we're not going to exactly get the right step every time, but since each step is pretty small, it's not that bad. And over time, I mean, over the whole course of the optimization, we'll basically stick to the right KL size. Actually, I see a lot of hands, but I'm pretty low on time, so I just want to get through a lot of my slides in the next 10 minutes, and then I'll get to it.
I don't understand, like, how does he
Okay,
get to
so
is this, like, isn't KL supposed to give you just the distance between the two distributions? How can you pick that?
So you use it to figure it. So you observe the KL divergence,
Yeah.
and then based off of the KL divergence that you observe, you increase or decrease its prefactor.
So you more or less it's like sort of a yardstick rather than.
Yeah,
It sounded like
you
you.
said it the other way.
Yeah. And then so what you end up doing is like if they diverge too much, then you just penalize them more.
Well, it's not that.
Yeah. Okay. Fair enough.
So if pull back lever is too high, increase
Yeah.
leader is too low, decrease leader.
Yeah.
So like, and I think the idea is that the KL maybe I'm wrong here, but I think the KL divergence is kind of a measure of our exploration. Like what kind of new policy are we trying? Obviously we've got this balance, right?
Yeah.
If we go too far and change our policy too much, then we're screwed because this important sampling term becomes very unstable. But if we change it too little, then we're not really doing anything. So then the idea is that if the collect lever is too high, we want to rein it in a bit by increasing this constant. And if it's too low, if we're not changing our policy much, we say, all right, yeah.
So it's. I was looking at it. I misunderstood. I thought it was going to be one or the other, either regularization term or like I guess sort of trying to fix the learning step size, the learning rate. But it seems to be like a hybrid of the two because you have regularization as where you crank down when it starts going crazy.
Yeah.
But at the same time, you ensure that it keeps exploring. So you have a minimum sort of learning rate, I guess.
Yeah, and look, you could do this with regular, ordinary L2 regularization as well if you wanted to, right? You could say, all right, well, you could apply this idea.
Happy people.
It's totally fine to interpret KL. It's just
see you tomorrow.
but this trick that I think is the new bit of TRPO.
Yeah, and so one of the things that is missing here is that you can also, on top of this, add an entropy bonus.
Alright.
Where it's not the expected value of with respect to pi theta alt, but actually pi theta. So it's actually the entropy of pi theta.
And that's just further.
Yeah, so then you can just say like so this basically tells you the observations that I'm getting I can trust. That's what the KL divergence regularization is for, and then the entropy bonus is just to make sure that the policy keeps exploring.
I haven't looked. I don't know. Is that PPO too, or is that
yeah, that's also
some flavor?
I think PPO is basically this whole subclass of things, but PPO. What usually people mean by PPO is not this, but the clipping version.
Oh, I see.
And then adding entropy bonus.
Yeah. Okay.
So just checking Shin, you know what entropy is.
I think entropy is probably the most understandable term.
No, that makes sense.
Okay,
Cool.
great.
So I think I
Just
just
question.
Yeah.
It's a bit unclear here. Like let's consider the very first time step. I mean update, right? Where our theta equals theta old. And then don't constrain the update step. We don't constrain step size in this case, right? So we still can screw completely within the first update.
Right.
Yeah.
How do people deal with it?
Well, I guess that's always a problem in whenever. I mean, that's just a gradient descent problem. If you choose a very big learning rate, then you're always going to fuck up at the very first step.
Alright.
I think is that what you mean?
Well, yeah. I mean, it's not a
Yeah,
solution,
but you also get no regularization term, right? So if you wanted to, you would infinitely penalize it. Is that what you mean? Because you would get a KL of 0 if you have no old policy yet, right?
yeah, that's what I mean.
Yeah.
I mean, just like the algorithm goes like that.
Yeah.
We just do some kind of like AND rollouts, right? Then we have our P theta old, and before update our theta equals to that, right? So we don't have any constraint right here, and this ratio equals 1. So basically we're just solving the classical reinforced kind of object policy group. And does not we still can just follow the cliff.
Couldn't you? But wouldn't you just, as decision problems being brought by organization, you would just have two starting policies, both randomly initialized, and then one is your old, one is your new, and then you just take it from there. And as soon as you've got past that point, your new policy becomes your old policy.
Maybe this is why the entropy bonus comes in handy, because like even if you do fall off the cliff, you've got your entropy bonus, which means there's going to be a bias towards policies that explore. And so even if you have a shitty policy to start with, hopefully by chance you'll eventually stumble upon something that yields some sort of return, and then the gradient can get going. Also during this process, this KL will become less and less.
Oh, actually, wait a minute. Does it actually have to fall off the cliff? Because you don't just, like, falling off the cliff would be useful, yeah? But what if you have Montezuma's revenge, and you just hop around that dumbass first screen, and nothing happens for a long time? Yeah, how do you upgrade anything?
Well, I think the idea behind this is sort of the Achilles heel, and I love these reinforcement learning algorithms. This is why I love the.
Oh no, that was so much better.
I want to get onto this sort of learning from experts thing at some point. But yeah, like this is just a general issue, I think. If you don't have any sort of winning trajectories that yield a return that is non-zero, you have to kind of blindly stumble onto that the first time.
Yeah. Would it be useful to penalize at the, I don't know, but then we would have to change that. So I was thinking about something, anything that has sparse rewards. Could you say that if I have reason to believe that this environment will give me sparse rewards, then I'll just automatically start by defining negative reward per time step, just as a default.
That's one way, yeah. Another way would be this sort of curriculum learning, where you just basically you kind of take a linear combination of different trajectory of I don't know the word.
Sounds like it's been a long day.
Yeah, objectives. So you can say this paper, like one of the papers, for instance, if you have something that you want to kick a goal, like a soccer thing, you first want to make sure that your agent is able to stand. So so the first objective that you give it in the curriculum of objectives is to make sure that its head is sort of at the highest point, and it just learns to stand up because that makes its head stand up. That's obviously has nothing really to do with kicking a football, but that's one way. Another way is to give rewards depending on how surprised it is to see a new state. So you can say like if
curiosity. Is it like based on curiosity thing?
Yeah, exactly. So then if it gets to observe something that it hadn't expected, then you get a reward. Just the novelty of it.
And to be clear, this is different from the entropy bonus.
Yeah. This is really how you feed in A's.
Right.
So that's has nothing to do with how you model the policy.
So is there would you say that you get would you do this, for example, in a practical sense, would you do this with like an environment wrapper, for example, in the gym, where you say for your first couple of steps, like for your first 500 steps, anytime like in breakout, for example, anytime the ball leaves the breakout, you give a large reward and you reset the session, that sort of thing? Is that?
Yeah. You can just do it as a wrapper.
Okay. How? Because that feels a bit more like a different kind of guidance than actual expert line, sort of like imitation line.
It's like I was thinking drawing the analogy to like training a dog. I think that curriculum learning is like exactly like dog trainers do when they want to, what they call it, shaping.
Yeah.
And I think the imitation learning is like a dog watching another dog do something.
Yeah, and that inverse RL is basically trying to do that in an automated way.
Right.
Yeah.
So they're both useful. Well, shall we continue?
Yeah.
Bad. And over time, I mean, over the whole course of the optimization, we'll basically stick to the right AL size. Actually, I see a lot of hands, but I'm pretty low on time, so I just want to get through a lot of my slides in the next 10 minutes, and then I'll get to the questions. Okay, so it's also worth looking at what's the connection between the trust region problem we're solving in TRPO and other reinforcement learning methods. Okay, as I said in the last slide, if we do this linear quadratic approximation, we get the natural policy gradient. If we do no constraint at all, then this is just normal policy iteration. That might not be totally obvious, but if you look at what policy iteration is doing, it's just you're just you're choosing a deterministic policy each iteration in which you choose the action that has the highest advantage according to the previous policy. So if you have no constraint at all, it's just policy iteration. And if you use a Euclidean distance to constrain your step instead of using a KL divergence, and then we do the linear quadratic approximation again, then we end up with just a vanilla policy gradient. That's you can just write it, go through the logic, and you'll come out with that result. So okay, this has some limitations though. So one issue is that it's hard to use in architectures that have multiple outputs. Like if you have, if the policy is outputting action probabilities and the value function, then it's not clear what you should use instead of the KL divergence, because the KL divergence doesn't tell you anything about how you should update your value function part. Empirically, it performs kind of poorly on tasks involving deep convolutional neural nets and RNNs, at least on certain benchmark problems, like the Atari benchmark. So I don't know exactly why it's true, but it might have to do with diversity, but that's not the full explanation. And third, the conjugate gradient makes it a little bit less flexible than if you just had to do SUD, and it makes it more complicated. So I want to talk about two alternatives to TRPO that do something similar in that you do something like the policy gradient update, but you do a more sophisticated kind of update step, and you're trying to constrain the size of the update. But I'm going to talk about two alternative ways of constraining the size of the update. So first way is there's this method called KFAC, which is actually pretty recent, but the idea here is we can make an approximation to the Fisher information matrix, which actually exploits the structure of a neural network. So in particular, you find some kind of block diagonal approximation of this matrix, where each weight matrix in the neural net is treated as its own block of parameters, and then you assume a certain kind of factorization. You assume that this block has a factorization as a tensor product of two other matrices. So it's actually quite simple. You assume that there's an alternative expression for the Fisher information matrix as an expectation of outer products of grad log probability. So then you write out what's the okay. You look at actually I'm kind of running out of time, so I'm not going to go through all the details. But anyway, you write down what the actual Fisher information matrix is. This expectation, which involves a product of four things, and then you just assume that it factorizes as you assume the two things are independent, and then you have some factorization, and this lets you this this is actually lets you efficiently compute and estimate this an approximation to the Fisher information matrix. And using this approximation of the inverse Fisher matrix, you can do a natural gradient step in the same manner that we described previously. And all you have to do extra in terms computationally is you have to maintain running estimates of a couple of covariance matrices, and then you periodically compute inverses in these matrices. There's an algorithm proposed or published a couple weeks ago called Actor, which combines this K-back idea with A2C. Basically plugs in the K-back natural gradient into the actor-critic algorithm A2C, which is like A3C but without the asynchrony part. And it's basically a pretty small amount of overhead on it, but it works a lot better. The limitations are it's less straightforward to use when you have parameters being used multiple times and with the but it can probably be used in these cases also.
So you said that to end around that?
Another algorithm is proximal policy optimization. That's what I just described before, where you use a constraint. As it turns out, this version I described before with the adaptive penalty is okay, but it's not the best possible thing. And something that works even better is to write out a certain kind of objective that involves writing down this important ratio like we did before, but flipping it so that it doesn't go. So you're basically saying, I don't want to change the probability ratio too far away from 1. But that itself wouldn't be exactly right, because then you wouldn't any longer be optimizing a lower bound or pessimistic bound on the policy performance. So what we do instead is write down a certain kind of element-wise minimum between the flipped objective and the unflipped objective. I'm low on time, so I'm not going to be able to explain it fully, but basically it's another kind of lower bound objective, which empirically works pretty well. And you just, this is a pretty easy thing to implement, because you just write down your vanilla policy gradient implementation, but then you switch to this weird looking objective and optimize that for many steps of gradient descent instead of just one step. And that way you're getting more information out of your data. And you're doing an update that's actually kind of achieves a reliable amount of scale divergence between the new policy and the old policy.
Much more. I'll do more in the morning.
So yeah, anyway, this pretty simple pseudocode. It's a lot better. Well, it's a bit better than TRPO on continuous control problems like these robotics control problems, and it's a lot better on these image-based problems like Atari, where TRPO is really bad on those compared to A2C, whereas PPO does better, as does Actor from the previous slide. And it's compatible with RNNs and multi-output numbers. Okay, I'll send out the slides, so here's some extra citations on the stuff on this slide. Let me actually just show you a cool video, because everyone likes cool videos. So here's a policy. We had a blog, OpenAI blog post for this algorithm PPO, and we trained this humanoid to run around. Actually, you can. This environment is available in the repository called RoboSchool. So you can actually do this yourself. And we also released the code for PPO, so you can basically you can train a policy to do this yourself. Though we didn't release the exact training code for this because it was messy. Anyway, you see that this guy is trying to run towards the red ball, which gets randomly placed in around every 10 seconds or every few seconds, and meanwhile, it's getting pelted by these cubes that are being thrown at it. And it's able to get up off the ground and also steer towards the red ball. It's not perfect, so it can sometimes it gets stuck on the ground for a few seconds and so on, but it's actually pretty good. And it can recover from getting hit in all sorts of ways. And yeah. So yeah, I don't know. That's up to you to decide. I think
Is that the
there's
same
some
one
interesting
where
questions
people
there.
actually created it?
Let's see. Oh yeah, when we do it without the pelting, then it can actually basically run perfectly and it never falls over. With the pelting, it's a little harder. But this guy, like,
actually training the
nice.
model was
Oh yeah, we can also, after we train that policy, we can just, I just wrote a little script that we can throw the ball on the keyboard, and then even though this is a little bit out of sample, because we never trained it for this exact distribution of tasks, we can do this perfectly well and run around when you control it. So you can imagine some video game where it's actually fully physical and everything. And you can also
But it's also like even when you're
use
kind
this
of
on
like
a more realistic looking
not do
robot,
these kind of
like the Atlas
things
robot.
at work, like when you go to like another
This
site.
is all these like
It's
really
just
cool
kind of
results are from
yeah,
like
you get more out of it.
polygold
So,
that we trained on very small.
They could have actually just held it on site, they just
Yeah.
did it.
Okay, we also have a blog post recently on this actor method I was talking about. And we have some code we have some code for a bunch of these things. Like we have A2C, actor, DDPG, DQN, BPO, and TRPO. I'm going to add some more tests to it, and it's some more documentation, but it's up there, so you can use it if you're willing to dig into the code a little bit. To train, actually, the humanoid who's running around and getting pelted by things, I think that was less than a day to train it on one machine that had about 32 cores. Okay, so I'm wrapping up. Let's see. Yeah, that's all. Questions? Thank you.
So it's 5:30 and he does have, I think this is one of two or one of three videos. So the idea was that if this didn't give us enough juice or there were no questions left, of course there aren't. The caliber of people who come to this meetup is as usual absolutely dazzling. But I think there's more than one video on policy gradient. So if you want to, we can get started on that, or maybe do that next time, or just have a chat about what would be the most interesting thing to do. Because I remember you said you're still working on the article for not Breakout, for Connect 4?
Yeah. I haven't gotten very far.
On what?
So I'm doing Alpha Zero.
Actually, we haven't had a chance to introduce ourselves. So, well, I think your face looks familiar. I think you've been here before.
No, this is the first time.
Fantastic.
I'm really
Awesome. So we've got three new faces. Everyone knows Patrick. Maybe you start with introducing yourself.
Alright. I'm Patrick. I'm a data scientist at Eliza. I do stuff.
Jiu-jitsu.
Which is why I have to go.
And which is why we can't stop him from
Yeah. And yeah, I think this stuff is really cool. I'm just interested in reinforcement learning from an academic perspective. Alright.
Cool.
Enjoy. Thanks.
See ya.
See ya.
Yeah.
So I'm Dennis, PhD student at RMIT, doing exactly this thing, almost. So my project is about in particular to speech synthesis, which is basically we do have a simulation of the human vocal tract with the tones of moving parts like tone, lips, jaw, and all that. And so we can move them, but we don't know how to move them in order to produce a sensible sound, right? Like a human-like sound. So I try to tackle this in terms of that.
Cool. I'm Pat. I'm an engineering student at Monash. Just looking to apply some RL to hopefully some robotics programs.
Yeah, hi, I'm Michael. I'm also a data scientist with Eliza, but Jiu-Jitsu is not mandatory here, so I don't do any of that. And I think RL is very interesting. It's going to be quite a huge role in the future. So I find it absolutely fascinating. Thank you.
Hi, I'm Robbie. I'm studying faculty of voluntary at Federation University, but I'm doing, of course, self-learning, so just going through machine learning and blockchain technology, going back and forth, and trying to implement in one of my based projects, which will be starting from the next semester.
So would you apply RL to the blockchain?
So I have no idea how I'll implement it, but at the moment I'm just learning blockchain by some like a group study, so that I'll be but because my project is basically creating a mobile application that I'm trying to implement blockchain on it, so that and especially I just recently learned proof of application, which is blockchain technology to provide a supply chain management system with the exact location of the supply and resources, where the resources are, so that it wouldn't get stolen or counterfeited by any other sources. So yeah, I'm just trying. So.
Some jobs then analytics super, and yeah, also find it interesting, exciting.
I'm Chris. I'm a data scientist at Microsoft. I'm just interested in RL because I'm not sure what I'm going to use it for yet.
I think I've got 8 minutes before I miss my train, so.
Yeah, right. Is it 3 times?
I'll go happily take all my
Yeah, so I also have my own sort of project where so I try to create something like scikit-learn or Keras for RL.
Like RL Leap, you mean?
So there's a couple of so there's the TensorFlow, what is it? TF agents. There's Keras RL, I think. There's baselines, which is pretty good actually. Yeah, that's all. Yeah. And then there's also the spinning up, which is also by OpenAI, where they have stripped a lot of the complication from the algorithms, making it even easier to read, which is really great. But all of these things still have so the way you use it is by basically forking and hacking. So it's sort of the fork and hack method. And I was so my goal was to not have that, but to have more like a more modular way of like using, like implementing RL basically. So I've implemented a couple of standard things already, and so Alpha Zero is the next thing because I thought people.
Does it work?
Well, the stuff that I've implemented works. Yeah.
That's already a good achievement.
Yeah, I can present some, but I think I'll just hold out until I have the Alpha Zero.
Fair enough. Okay.
Yeah.
I was thinking maybe the other way around would be interesting if you could get your hands on it, and you could probably kick the tires really good on that, and see whether it works. Because currently I'm still trying to finish my the Russian course that I've been doing, which I've been very, very lax on. I'm sorry, Alex, or Pavel, if you're watching, which you're probably not. But yeah, Patrick and I have been trying to program just reinforce itself just on that. Coming through last day or something.
Okay.
It's pretty cool. It's good fun.
Yeah.
And it blew me away with Breakout. I tried just DQN, and it took forever. It just didn't get anywhere. And the moment you add experience replay, not just simple experience replay, like nothing fancy, it just took off. Bam!
Yeah.
Fantastic. Yeah.
And then just doing DQN.
Literally. This one was just a exploring.
Yeah.
Yeah.
Boom, boom, boom.
Yeah, exactly. So, that difference was just, I think my average reward was like somewhere between 8 and 12, sort of whatever, and then suddenly it got to like 27, and the next one was like 45 or something as soon as I added experience replay. Just the difference was
Honestly, try out BPO, because then it's like all of those extra sort of pieces. It's kind of, it works quite well on Atari as well. So it's like, anyway, sorry.
Oh, no, that's alright. Okay, so my name is Shin. I'm the machine learning engineer that just joined Alice, so to speak.
Oh, right.
But I've been doing machine learning computation for a while. And I did have like some exposure to the introduction of RL before. And sorry for the dumb question at the beginning. I forgot about the expectation thing. Thanks, Pat, for reminding me of that. Now
we have to think about it.
Now it all comes back together. So I just think that IL is very fascinating, and I don't know whether I would love to go into robotics, but I'm not sure whether I'm in this field. And IL seems to be like something aligned along with that.
Is there a vote?
So I just think that I'm just fascinated by it. And I'd like to learn a little bit more on that.
Cool. Right. I must admit I was a bit disappointed by this particular lecture. I didn't feel like this was telling us too much that we didn't know. I thought it would give us more of an underpinning with respect to the PPO stuff that we looked at before. But
I feel, so the real interesting bit is like how they implemented TRPO, I think, which is it's just really cool. It's just not really practical, but it's really cool. It's really amazing. Like from a theoretical perspective, I think it's really cool. But
and then whole videos about TRPO in the very end. He just says, actually it's better. It's easier and better, just use it.
Exactly. This is a 40-minute video. The last 39 minutes were just, bit fancy, but use this.
Yeah, and I think the disappointing part those PPR is like all this
but my dog is sick for
not
the
deviating so much from that performance ratio. I think all these theoretical methods they ended up clipping like a very simple ended up being on par performance wise with all those theoretical methods that have theoretical underpinnings. That's a fascinating actually.
I think so. Like the bird's eye view of it, I think is pretty cool though. So it's like basically instead of penalizing, if the objective sort of goes in the wrong direction, instead of penalizing it, by clipping you kind of remove the incentive for the algorithm to go towards that anyway. So instead of sort of patching up the mistake that it does by instead of patching it up, you basically just kind of remove incentive. Which I think is a really, I wouldn't have been able to come up with it, I don't think. But it's like, it's really cool.
So, with regard to the next session, there are a couple more videos in the Deep RL Bootcamp. I'm not sure whether the SVG or stochastic computation graphs would be so interesting for us, or whether maybe the Frontiers lectures would be cool. But I feel like we haven't looked at the book for a while, and I wonder if it makes sense to go and check out. So there's the Looking Deeper chapter with applications. I'm not sure if there are, and similarly there's a Frontiers chapter. I'm not sure if there are chapters that would build on what we've just done, and then at the same time give us the opportunity to get some more theory underneath, and some deeper explanations, especially some of the. I must admit, I couldn't follow the notation. It was just a bit too fast. But in general, sort of get a bit more of a fundamental.
Oh, thanks, man.
Optimization for continuous actions. I think we definitely haven't looked at that. I think we haven't looked at
mean standardization.
That's usually what they do,
Well, that's good.
the whole continuity stuff, the whole continuous problems.
Yeah.
On the other hand, now that you're here, would you be interested in giving a presentation maybe on what you've seen and what you've done so far in terms of your research or in terms of your project, if you're allowed to do that without knowing this?
Yeah, I can do that.
But, yeah.
I just don't know why, when, because, yeah, but if you give me some time, I'll let you know.
Sure.
Once I'm done.
Yeah, because it's always interesting, I find, for us to see what people are doing with it, because my sort of go-to example was always the Google optimization of their air conditioning system, which saved a lot of money. But the more recent one that I found was this oil field control system. I couldn't get the paper, unfortunately. But there was water flooding optimization in petroleum reservoirs. So it seems that a lot of control problems in the real world, especially in more complex state action spaces, are better controlled with reinforcement learning, if you can, I guess, model the situation well enough. Then
it's quite interesting. There was like a small meetup, and there was a presentation from a guy that was actually solving. There was consultancy, and they were solving optimization problems, and so. And I asked him like, oh, it looks like something that reinforcement learning could work on. And I said, no, because we don't look at that, because with the optimization we have the mathematical guarantee of what that works, and we can sell it to the clients, show it to the clients that that's basically reliable and something they could sell. That's what they were not interested in.
Yeah, fair enough. But isn't the whole idea that you use it in a space that's noisy? So the more noisy your space gets, the more brittle your optimization is. So
it's very different. It's the guarantees of control.
Is that human hubris though? Like, I don't know about you guys, but when I drive, even just through the city with my wife, I apparently make mistakes all the time.
How would you know?
Yeah, but I assume the same goes for everything. So we
that's kind of a joke, but that's kind of like actually the point. Like how do you you have to put this in like a safety critical system. How do you know it's not going to go just on policy, just like into a situation that's never seen before?
Oh, you mean okay? So your issue would be transparency and reliability.
As an engineer, you sign it saying this is reliable. This is this. You got something.
But I think just on a reflection, I think it probably depends on complexity. If the problem is too complex, like self-driving car, then you need to rely on those things, and you cannot program it.
Yeah, and there you have this case. I'm making a lot of friends by constantly saying that I'm totally annoyed by this question about whether the car should kill the grandma or the kid, because there will already be fewer grandmas and fewer kids killed when we have self-driving cars. It's not to say that it should do either or anything, but I wonder whether they're asking the wrong questions in these sorts of spaces, whether we're not optimizing for the wrong thing, or like focusing too much on the wrong thing.
I think it's more like a philosophical question than an engineering.
Yeah, it sounds like trolley. The trolley effect.
Yeah. So
I think there was like a
vegetable. Why are we discussing to kill the grandma or the kid?
Oh, I think that was the sort of sad example. That's like the new trolley problem. Is like sort of the self-driving car has to decide.
I remember like actually afterwards reading on internet, and I think it was mentioned that they made a public statement, but I don't remember what it was. But they declared that car will do this. So. Don't remember what it was exactly, but they openly said what the behavior will be.
Because at the end of the day, it's not like you can't not decide. Yeah. So you have to pick one, but it's a silly example because that is a very particular situation. That's not what the world's like.
Yeah,
You
and
know?
I think on a
So-
one occasion during one of the meetups there was this problem. Yeah, who is responsible for the behavior of the car?
Developers or anyone else, yeah.
And I think we just like
Uber itself, for example. Did happen in California, right?
but
the Uber
but
car accidentally killed a
But-
woman, right?
Yeah, cycle.
yeah. So but we were.
They were doing the worst stuff. Like so,
Yeah.
their car wasn't. It kept sort of detecting phantom objects, and so applying the emergency brake. So instead of fixing it, they turned off the emergency brake, and so the car couldn't actually activate the brake.
Things like Chernobyl.
Yeah, the guy
turn off
got-
the
I was
safety system. I thought those moments are behind us, but still. Oh yeah, and going back to that meetup where we were so puzzled with this concept, who is responsible? And actually, soon afterwards, those banks crashed, those 737s, where looks like there's some software issue that may be responsible for that. And that's exactly the same thing. People died because of the looks like malfunction of the plane. So.
But if I
Like,
remember, I might be mistaken about this particular problem as well, but if I remember correctly, that was also a thing where Boeing knew and they told the pilots to, in a different video, to do it in a certain way, and it was kind of opposite to the way the pilots had done it before or something like that. So it's not like Boeing got away scot-free there. But I might be remembering this completely wrong.
Same sort of thing.
Yeah.
That they sort of didn't train the pilots well enough.
Yeah.
And then when this thing sort of kept the plane pointed up.
Yeah.
Sorry, it pulled the plane down.
Yeah.
Because they changed the engine configuration.
Yeah.
But they didn't tell the pilots about it, and so when say one of the settings broke and the plane was tilting too high, it would go down.
Yeah.
The pilots didn't really know what was going on, and they fight against it.
Yeah.
Eventually, you just lose, and then once it's straight back down.
See, pilots, policies, what big of a difference in that case?
They could, I guess, they didn't have much of a chance there, I suppose, but yeah.
I thought it was the pilots couldn't override what is written in the software as well, right?
Yeah.
Yeah, so basically, even though they didn't know, they couldn't do much.
They couldn't even turn off the system as well.
Like, another Chernobyl.
Yeah. Okay, so I'll schedule you for like maybe 2 or 3 weeks if that's okay with you. Does that work? So it would be interesting just to see like what you do and what.
Mine is more like model-based RL. So
okay, yeah,
like,
that was gonna be my
inverse RL, something like that.
Cool.
Is the model like completely getting out of hands? Like some organs like are not supposed to do that stuff, but they're like jumping around and stuff. Because you just said that now you have a complete model for the human, with vocal cords and stuff like that. Yeah. So are you like training the machine to like imitate the
human speech?
Yeah, human speech.
Yeah, I just give it a sample of someone like even me, like saying mom, papa, whatever, and then just plug it in the algorithm, and then it just goes for it, trying to.
Yeah, so it will also like try to visualize the way.
Of course, I do have
the model,
full 3D visualization.
Yeah. So in that part, when you try to try the machine to visualize that model, does that doesn't some part just go like crazy?
No, it's constrained, so it doesn't go.
Okay.
It still looks like
this
human vocal track. So
So they have like a limitation. So
range of motions.
That will be another interesting thing to do. I think we haven't looked at model-based reinforcement learning a lot at all. So and it's a pretty big thing. I think at the moment. Like there's a lot of.
It's just in between the model free, like typical RL and control systems, right? this is just like.
So I remember Andrew saying that, or like at least in his lectures that I saw, they were all model based. He didn't even bother with anything that wasn't approximating anything.
Yeah, because like in real life, you cannot run your environment or whatever it is just like for millions of steps. Like they don't mention it, but each of those environments just to be solved like approximately need at least like a couple of millions of steps. And for example, in my case, one step in my environment, in this bookclub environment, takes it just goes like in real life speed. So 1 second of my environment just it takes 1 second of computation. Quite decent machine.
Yeah.
So just imagine, just a couple of millions of seconds in this environment would end up in infinity in real life. So.
Or the thing with the helicopter trying to fly upside down. You only have so many helicopters.
Yeah, all like this.
Yeah.
Looks really promising.
Sorry?
It looks really promising.
Yeah, we'll see. I'll actually, how about I go and we start for next week. We look at the policy stuff that we haven't looked at before. I think the continuous stuff we haven't looked at, continuous problems, policy gradient for continuing problems, and then I'll find a paper so that we can get into model-based stuff more deeply. See what's been going on there.
Yeah. I was also thinking like maybe this what is it called, like DynaQ, and that's like I think it's chapter 6 maybe.
The one with the extra DynaQ and DynaQ Plus.
Yes, well, whatever the model-based, the thing that had planning in it as well.
Yeah.
So like I forget what so the problem is that at that point I wasn't interested in it. So they sort of went one like I don't know, just didn't really stick. So now I am interested in it, so I'd like to kind of revisit it. And then so there's also the multicolor tree search that I'm sort of doing.
That's the alpha zero.
Yeah, exactly. But that's but anyway, just kind of the planning step of model-based.
And I still don't understand how it really addresses. I haven't really invested much time in it. But I've just seen that there's actually Dutch traces and Monte Carlo lines.
I sent a few emails to what's his name? Rich Sutton.
Oh yeah.
Like the writer of the book.
Yeah.
And he just said, they're basically the same. And then I sent another. To give a little bit of background. Eligibility traces, if you have a function approximate, it looks very much like ordinary momentum updates.
Yeah.
It's almost momentum, not quite, but close enough. Anyway, so I sent him a message saying, like, do you know about this? Like, can you say something about it? And he's like, yeah, it's basically the same thing. So then I'm thinking, like, why don't you just, like, why is it included in your book? Because like the atom optimizer isn't explicitly included in the book. I think it's just for historic reasons. Honestly, I don't think eligibility traces is something that you need to pay attention to.
Fair enough. Okay.
I think it's just that's my. I can explain it a bit more about what I think about it, but it's basically that.
Right. So, and then there's also I still remember there's the approximations that you had found with the irregular resolution of continuous spaces. This overlapping.
Featurization stuff.
Yeah. So there's like tile coding for 2D state spaces and these sorts of things with the coarse coding, tile coding with this sort of irregular randomized tile coding. Yeah.
Isn't that the full quantization of continuous space?
Yeah. So that might fit together with, if we look at policy gradients for continuous spaces, and then also look at the feature construction. That might That might be helpful. So I'll look at that for the next 2 weeks, and then if you need more time, that'd be cool. Maybe we can have a short presentation as to where you're up to with the library at the moment.
Is it intensified?
Yeah, it's most. I try to use Keras.
Why not
Why?
PyTorch? Why do I use it?
Academic says use PyTorch.
People love PyTorch.
Because it's the best one.
So you have to actually put something on like the machine.
I don't know because Keras.
You just used to.
No, I mean I wasn't really used to anything, to be honest.
Oh.
Yeah.
Okay.
So I'm pretty much an open book, but yeah, I guess not anymore. But no, I'm definitely not stuck on. Like if I'm stuck on any framework, it's Open Web. To be honest. So yeah.
The platform agnostic.
Yeah, exactly.
Yeah. Awesome. Could you maybe pose your question, the problem you had, the one about the multi-classes?
Oh yeah, I don't know if anybody is still. It's already 6, but I do have. I'm working on something that I'm kind of. Well, I was kind of stuck today, so I'll probably figure it out tomorrow. But it gets figured out together. But so basically, I have a multi-class.
If we're digging into that yet, I will say goodbye to
Yeah.
people. And we are not revealing any work
State
secrets.